there are some typical specifications for the electric car, and one is the traction battery. The traction battery is about 300 volts, but this battery voltage varies quite widely. Is varying from 220 volts to 430 volts, and this is a new kind of a battery which is designed to give the extra mileage for the car. Then the other one is the drive control unit, which is for a typical urban car is about 65 kilowatts. And then a DC-DC converter, which is somewhere between 1.5 to 3 kilowatts, and the onboard battery charger, which is about 3 to 6 kilowatts. So now, coming back to the real power electronics here. So this is a typical diagram, and this diagram basically showing that what are the voltage, what are the various voltages and currents which is going through the system here. And so here we have the high voltage, high current system, as well as the low voltage, high current system. In the electric car, one of the major consideration is how do we do the cooling of the system, because as we have seen in the previous diagram, we are producing a lot of heat, and this is the electronics, so heat must be removed. So the cooling system is the integral part of the whole power electronics. And one of the system is basically which is a preferred system, is the closed loop system, in which there is a forced cooling, liquid cooling, that is going through all the three different types of converters. And I must tell you one thing here is that the power rating for the DC-DC converter and AC-DC converters are very small compared to the rating of the inverters. But if we really look at the physical size of these three converters are more or less identical, because the converters, which are DC-DC converters and AC-DC converters, they are very complex. They have a lot of passive components, magnetics, and so on. But the inverter, on the other hand, is a very simple one, and it does not have a lot of passive components. This is some of the basic philosophy, how to integrate the overall system, and then how we basically can remove the heat. And if you see here, this is the integrated system here. You see the three different heat sinks, and basically which is common cooling, force cooling, liquid cooling system here. Now, what are the main factors here? The main factors are to minimize the heat generation on these converters, or within these converters. Then other one is the minimize the size of the passive component, and there has to be ease of control, because one of the concept here is that the power electronics will be integrated in terms of the semiconductors, and when the power electronics is integrated in terms of semiconductor, so we have to have a very simple control. So now let us first consider the first unit, which is a DC to AC inverter. And in the DC to AC inverters, basically this is the block diagram, and as you see here, the main thing here is we have the power section, which is a three-phase full bridge circuit. We have the drivers, the controller, and some housekeeping power supply. So this is a very simple architecture from the power electronics point of view. these are the typical IGBT-based three-phase inverters, which basically producing the AC voltage and directly going to a electric machine, which is typically a permanent magnetic machine in the electric car. And as we see in this one, we have some EMI capacitor, and then we have this capacitor, bus capacitor here. And what we see here is that this is about 65 kilowatt system here. And if you look at the size of this capacitor, the size of this capacitor is more or less same as the size of this 65 kilowatt electronics model. And also, in order to increase the reliability of the inverter, because this inverter has to work for at least 10 to 20 years. So this is this is not the electrolytic capacitor. This is a polypropylene high frequency type of capacitor. And in order to reduce the size of this capacitor, which is quite expensive, actually the cost of this capacitor is almost 60% cost of this model here. So this is a very, very expensive capacitor. So in order to reduce the size of this capacitor, now we must have the switching frequency of this inverter as high as possible. But as we know that we are using the IGBT, then switching this IGBT at high frequency is not very practical. I think if we are switching around 10 kilohertz, then perhaps that is the right frequency. But if you want to switch them at much higher frequency in terms of 50 to 100 kilohertz range, to reduce the size of this capacitor, then there are a lot of heat losses during the switching. So the biggest challenge here is in this DC to AC inverter is to reduce the size of this filter capacitor while maintaining the high efficiency at the high frequency. So if we look at this is one of the conceptual drawing here. So these power losses are in the order of about 2 kilowatt. So this 2 kilowatt power losses must be removed by the liquid cooling. So now, if we really look at the for this particular application, the IGBT have the highest power density, and they are suitable for medium frequency. And MOSFET have the best switching performance, but at lower power level at high frequency. So now, what we can do is that one of the limitation of IGBT is the high switching frequency because of its switching characteristics. Then one can do is that you can combine the both MOSFET and IGBT together in the same package. And if you do that one, then what you can do is that initially during the switch on and switch off, you can turn on the MOSFETs, and then you can turn on the IGBT when the MOSFETs are on. So if you do that one, then what we can do is that we can rely on the switching characteristics of the MOSFETs, not on the IGBT. And thereby, we can increase the switching frequency in several tens of kilohertz. This is some of the comparison of the loss comparison. If you're just using the, let's say the IGBT, then these are losses, and if you're using MOSFET, then these are losses, and this combination of the two in the least amount of losses. But now, as we have seen that this is a classical three-phase PWM inverter which is providing the sinusoidal output. So